This conference will now be recorded.
Hello everyone, the topic that we are going to discuss today, VSEPR theory, and then there will be some VSEPR table where we will see how to draw the structures. And then there will be limitations of VSEPR theory because it is not always giving correct results. And after finishing that, we will see some problems also based on VSEPR. So VSEPR theory, when we are starting, we know that before this theory, one theory we have already discussed. First, we started this chapter with octet, and then there was Lewis theory. But in Lewis theory, there are some, that is, it is not always giving full correct result. There are some limitations. And compared to Lewis theory, now VSEPR theory, it is giving better result, because when you consider only Lewis concept of structure of molecules, you can get relative position of atoms in the molecules and how the electrons are shared between different atoms. But the problem with Lewis theory is that we cannot predict the shape of the molecule if you are using this concept. Now, if we combine Lewis theory along with this VSEPR theory, it will be better because it can now give us the opportunity to predict the shape of covalent molecules, and not just molecules. Sometimes if you have any polyatomic ions carrying some positive charge or negative charge, for example, carbonate ion. This is polyatomic ion. 1 carbon, 3 oxygen, 2 negative charge. So this is polyatomic ions, or it may be any neutral covalent molecule. So for this type of molecules, we can apply VSEPR theory. Though after after the discussion of this theory, we will also see some limitations. But before that, we have to understand what is the basic concept of this theory. So the full form is valence shell electron pair repulsion. So if you just take the first letter V, S, E, P and R. So valence shell electron pair repulsion, you will see that there are electrons involved in bonding between two atoms. So suppose you have two atoms, A and B. Sorry, A and B. So in A and B, when we are considering this covalent bond, there are basically two electrons. So this is bond paired electrons. But suppose there is lone pair over B. So these electrons are not taking part in bond formation. So that is why I am calling it lone pair. And remember, it is pair. So that is why lone pair. You can also call it non-bonding electron because they are not part of electron. Now, this theory is all about bond pair and non-bonding, that is, or you can say lone pair electrons. Okay. So how they are arranged, depending on that, we can get different types of shape. And also in the name itself, valence shell electron pair repulsion. So there is different types of repulsion possible between 2 BP, or it may be possible between 1 BP and 1 LP and 2 LP. So 3 different types of repulsions possible. So we will see what are the main postulates. Sorry. So what are the main postulates? The shape of the molecule depends on the number of valence shell electron pair. So that is why it is, the theory is called VSEPR. What is valence shell electron pair? Valence shell means where the valence electrons are present if you consider any particular atom in a molecule. Now the electron pairs that are present in valence, these electron pair, they can be used as in the bond formation, or they cannot be used in the bond formation. So when they are part of bond, you can call these electrons bond pairs. When they are not part of bond, they are non-bonding electrons or lone pair. Now when it is bond pair, electrons are shared between two atoms, obviously, as I have just shown between A and B. But when it is lone pairs, they are not involved in bonding. So that is the reason you can also call them non-bonding. Non-bonding. Okay. So these pairs around the central atom, they repulse each other, and hence to minimize the repulsion, they are located as far away as possible. So suppose you have any molecule. I'm just saying, suppose we have any molecule A and there are other atoms, but just focus on this molecule A because suppose it is the central atom. Now surrounding A, there may be some electron pair. So this is the electron pair which is present in bond. So this is bond pair. Some electrons may be present as lone pair. There may be another bond pair. Okay. Now how these electrons are arranged in the three-dimensional space, depending on that you can get different types of shape. Now this bond pair and non-bonding pair or lone pair, because of repulsion between them, because there may be different types of repulsion. See the next point, it is mentioned the order of repulsion between the electron pairs. Maximum repulsion will be there between two lone pairs. So suppose A is having another lone pair, so there will be some repulsion between this lone pair. Then the second type of repulsion possible between one lone pair and one bond pair. Okay, let me change the color. So this is one lone pair, this is a bond pair. So there is another type of repulsion possible. And between two bond pair also repulsion possible. So this is a bond pair, this is a bond pair, here also repulsion possible. But maximum repulsion is possible between two lone pairs, and they are also taking more space. Then LPBP, then BPBP. Remember this order? Now based on these repulsions, these bond pair and lone pairs, they will be arranged surrounding this A in a different way. But the purpose here is to minimize the repulsion as much as possible, because any molecule or any species, they always try to remain, or they always try to reach the most stable arrangement. So that is why they will try to minimize this repulsion as much as possible, and in doing so the final structure that will be reached, that will give you the idea about the shape of the molecule. Okay. So a lone pair occupies more space compared to a bond pair. Okay. Now next point, the last point. Suppose if there is a double bond. Here I have just drawn single bond, but it may be like this. Double bond present between A and B. So when double bond is present, or it may be triple bond between two atoms. Now when it is double bond, you know in one bond there is one electron pair. But when there is double bond, then another pair is there. Then if you consider triple bond, see, total 6 electrons, that means 3 pair. So obviously here, as the number of bonds are increasing and bond pairs increasing, obviously when you are moving from single bond to double bond to triple bond, the space requirement will be high. Okay. So double and triple bonds, they occupy more space and cause more repulsion, but cause more repulsion, but are considered as single bond while determining geometry. So in the statement it says that double and triple bond, obviously they will take more space because number of electrons are high. But when you will consider the geometry, then they will be treated as if they are also single bond. So right now this statement, if you are feeling that is little confusing, it will be gradually clear when you will actually see the examples. Okay. Now one by one we will see the tables. Now as we have seen that the valence shell, whatever electrons are there, they may be treated as bond pair or lone pair. So suppose for any particular central atom, the central atom is A, okay, and B is bonded atom, and here capital E means number of lone pairs. So see, this is the type of formula of the molecule. So when it is, suppose it is AB type, the most simple possibility. So when it is AB type, suppose A is the central atom and there are total electron pair present 1. Now this electron pair it can use for bond formation, obviously, because only one pair is present. So and one bond must be there. If it is there is no bond, no question of this, why we are discussing this theory. At least one bond should be there. Lone pair may be 0, that is fine. So as we have only one pair, so it will be used up in as bond pair, and lone pair will be 0. So in this case, what will be the geometry? The geometry will be linear. And the corresponding example here we have hydrogen. So suppose in hydrogen, though it is diatomic symmetrical molecule, but you can consider as if one hydrogen is A. Suppose this is one hydrogen, this is another hydrogen. So suppose this is A, this is B. So I'm just saying that you have to treat one hydrogen as central atom, another hydrogen as bonded atoms, or B. That is just compare with the general form. Now we know that hydrogen is having only one electron. So in this bond that is present here, there will be two electrons. So just focus on only one hydrogen. Surrounding it, there is only one electron pair, and that electron pair is bond pair. Fine. So in this case, it is a linear geometry, and this angle is obviously 180. So that is also mentioned in this step. Now the next possibility is obviously two electron pair. Now when it is two electron pair, there are two possibilities under this. So see, this is the first row, this is the second row. So when both the electron pairs are treated as bond pair and lone pair is 0, the type is AB2, then also it is linear. Angle 180 degree. Linear means always 180 degree. And corresponding example, you can take example as CO2, or another example is also there, you can consider BeF2. So see, when it is linear, this is a central atom, this is one B, this is another B. So the type is AB2. Don't look at the other structures, just go with me one by one. Okay, AB2. So when it is AB2, it is linear. These two pink atoms are B, central one, the blue one is A. So you can consider as if A is carbon and these two are oxygen. Now here, though it is true that double bonds are present, but one is pi, another one is sigma, you can focus only on sigma, because when it is, though it is double bond, it will take more space, that is true, but it is just like as you have seen in case of hydrogen, it will be treated as single bond. Now carbon, if you consider the number of electron pair, two electron pair, this is one electron pair, we use another color, this is another electron pair. I'm not considering the pi bond, just focus on sigma bond only, because we are just focusing on the position. In the same position, there is pi bond as well as there is sigma bond. So both the positions you cannot consider. Okay. So don't focus on pi, focus only on sigma. So there are two sigma bond, there are two bond pair. So one bond pair for one oxygen or one B atom, another bond pair for another oxygen or another B atom. So the type is AB2, and this is the example. You can also take another example, suppose BeF2. So Be, it is group 2 elements in valence electrons total 2. So these two electron will be used up for bond formation with fluorine, and another electron will be coming from fluorine. But surrounding beryllium, how many electron pairs are there? Total 2. So this is also another example of this type AB2. Now come to the second possibility. If out of these two electron pair, one is treated as bond pair, another one is treated as lone pair, then the type will be ABE, because E means lone pair. So central atom A, that will be in the middle position. One side, this is A, this is E, and this is B. So on one side there will be a lone pair, another side there will be B atom. Corresponding example you can take cyano. So carbon, here also we have two pi bond, but just focus on one sigma bond. And in this sigma bond there are two electrons. So carbon, here one, that is, this is used as one bond pair, another, that is a non-bonding pair, another electron pair that is present like this. So this part is actually this part. Try to find the analogy. This is the central atom and this part is C bond N. Don't focus on whether it is triple or double, because they are treated as if there is only one. We are ignoring the pi bond. Okay. Now we will see the next possibility, which is sorry, not possibility. The next, after one electron pair, we have seen two electron pair. Now we have reached 3 electron pair. Now when it is 3 electron pair, it may be that all the 3 electron pairs are bond pairs. So the type will be AB3. There is no lone pair. No E is there in the general formula. Okay, I forgot to mention that in all the 3 examples that we have discussed, in all cases it is 180 degree. So you can understand this angle is 180 degree. This angle is 180 degree. Okay. Now we have reached electron pair 3, and under this the first possibility is all the electron pairs are if they are bond pairs. So the type will be AB3. And when it is AB3, geometry is triagonal planar. Okay. And we will see the picture. So you can see triagonal planar, all these angles are 120 degree. So if it is A, this is B, this is B, this is B. So this is triagonal planar. Okay. And corresponding example, you can take AlCl3, just put A aluminium in the middle position, central atom A, and put 3 chlorine atoms in the positions of B. You will get same type of structure. Then another example possible is SO3, sulfur trioxide. That is also triagonal planar. But we will also see the next possibility, which is if out of 3 electron pair, only 2 are used as bond pair, and the rest that is left, that is treated as E. So now the formula will be AB2E. Corresponding example is SO2, and you can also consider ozone. And there is a little difference in angle. So when it is triagonal planar, that is you do not have any lone pair, no non-bonding electron, only bond pair. So in that case, it is the ideal angle 120 degree. But suppose if it is SO2, so now you can see this is SO3. The angles are perfect. Okay. But now, if one of these position, there is now lone pair, so it will be now SO2. So what will happen now? This angle, it will be slightly shrinked because there are electrons here. So there will be LP BP repulsion. So because of this LP BP repulsion, you know LP BP repulsion is always high compared to BP BP. So in the previous structure SO3, you do not have any LP, you just have BP BP. So repulsion is less. Now when you have reached SO2, from SO3, there will be one lone pair and LP BP repulsion, which is higher than BP BP. So that is why this angle, it will be slightly less, 119 degree. Fine. And there is another example of ozone also. Remember the structure of ozone, probably in the previous class when we have discussed how to draw resonance structures, there you have already seen the structure of ozone. So how it is? So 3 oxygen atoms, it will be like this. Positive, another resonance structure also possible, but it is equivalent. So this is also under AB2 type, because surrounding this middle oxygen, it is as if A, this will be treated as B, this will be treated as another B. Okay. So the third position, there is no other B. So that is why it is not AB3, it will be AB2E. So after 3 electron pair, next possibility we will see. Okay, one thing I would like to mention, that is not given in the table, but suppose there are 3 electron pair and this is central atom, this is B, and it may be that another possibility, it may be A2E. That means the formula now it will be ABE2. So it is just analog of triagonal planar, but triangular planar is the first structure where all the positions there is some atom. But suppose one atom you are now replacing with a lone pair. Then the next possibility is now you are replacing 2 B atoms with 2 E. Okay. So what will happen? From triagonal planar, it will now shift to bend and then it will shift to linear as you are increasing E. That is as you are increasing lone pair. So basically, ideal structure is, that is you can say geometry is diagonal planar, But if you ignore lone pair, without the lone pair, just focus on this part. Don't you think it is bent? Come to the next one. Without this E, if you focus on this part, it is just like linear, as we have seen in the first examples. So under trigonal planar, if all the positions there are atoms, maximum positions 3, all the positions atoms, it will be trigonal planar. But as the number of atoms are decreasing, that is omitting the lone pair, the remaining structure or shape will be bent or linear. Right? Next is electron pairs, total 4. Now under these 4 possibilities are there. The first possibility is AB4, where all the positions there is some bond pair and there is no lone pair, it is 0. And the corresponding geometry is tetrahedral, angle is 109.5 degree. Very good example, CH4. Now the next possibility is if one of the bond pair, now it is less, and that is now lone pair. Formula will change from AB4 to AB3E, and it is no longer tetrahedral. That is, if you omit the lone pair, it is no longer tetrahedral. Now it is trigonal planar. Angle is changed. Corresponding example also you can see. So here you can find similarity with the formula AB4. A is carbon, B is hydrogen. AB4, CH4. Then you can find similarity of formula PCl3, AB3E. So there is actually lone pair, but that we cannot write in formula. So PCl3 means AB3. H2O. So this is A, 2H means B2. So it is AB2, but we cannot write E in formula. Okay. And the last possibility is 3 lone pairs, only 1 bond pair. So now the formula will be chlorine. So if you write chlorine in this way, one chlorine you can treat as if it is A, another chlorine you can consider it as if it is B. So it is matching with this formula. So these are the general, that is here any specific elements or atoms are not shown. This is the structure. So this is tetrahedral, that is AB4. Now it is AB3E. So this is actually E. In the next one, AB2E2. And the last possibility, ABE3. So you can consider as if it is chlorine. This is another chlorine. And these 3 are lone pair. Then in the bent, as if it is oxygen, H, these 2 are lone pair. As if it is PCl3, it is Cl, 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 and this is CH4. So CH4 you can see, this is tetrahedral, all these angles are same, which is 109 degree, 0.5 degree. Then we have NH3. Now NH3 is basically just like PCl3, it is under the type AB3E, where N is A, H is B, and this is E is lone pair. Fine. So this angle, now see, it is not the ideal angle of tetrahedral. Ideal angle is 109.5 degree. But now because of this LP BP repulsion, the angle will be slightly lesser. So now it is 107, like this. Though molecule to molecule it may change. In PCl3 it is written 107, not necessary it will be exactly in case of ammonia, but it will be close to that. It cannot be like methane, because in methane there is no BP. So there is no LP. So LP BP repulsion, that question doesn't arise. Next you can see here water molecule. So this is A, this is B, this is B, E, this is E. Now in this case the angle is further reduced because number of bond pair increased. More is the bond pair than LP-BP. So in this case basically LP-BP repulsion, you can find both sides. So now this angle is further reduced compared to the ideal angle of tetrahedral geometry, which is 109.5. So I hope in this slide there is no doubt. The next possibility is electron pair 5. After 4, now we have entered 5. So under 5, see, gradually we are decreasing the bond pair and gradually lone pair number is increasing and the formula is also changing accordingly. AB5, then just reduce number of B and increase E. So AB4E, AB3E2, AB2E3, and the last one ABE4. So these type of examples are very rare, so you can see there is no example, but possibilities is always there. So come to the first one, which is AB5. But simultaneously, if you see all these together, the first one, that is where no E present, no lone pair present. So all the positions, all the 5 positions, there will be atoms. So this is A, and as if all these are B, AB5. So here the structure that you are seeing, it is triagonal bipyramidal. So why it is triagonal bipyramidal? Because if you just join all these positions, you are getting a triangle, right? Now after getting this triangle, if you now join this position, as if you are getting a pyramid, you can also get a pyramid in the lower portion. So first draw a triangle where all these angles are 120 degree, and if you consider this angle, that is this is axial and all these are equatorial. Axial A and all these are equatorial, 3 equatorial. So the angle between one axial and one equatorial, this angle is 90 degree. So that is why 2 different angles are mentioned here in the table, 90 degree and 120 degree. So this is 90 degree, but this angle is 120 degree. Fine. PCl5, that is a very good example. Next come to the AB4E type. So in AB4E type, now what will happen, which is basically a case under triagonal bipyramidal. So from triagonal bipyramidal, if you just remove one position, okay, so the remaining position, that will be seesaw. Now seesaw, let me draw it here. Suppose I am drawing PCl5. Okay, this is a triangle and these two are axial. Now suppose this one position, if I remove, so you can find the corresponding example. It is SF4. So in SF4, one position is not there, but instead there will be a lone pair. And remember, lone pairs, as it is taking more space compared to bond pair, so it will always be in the equatorial position. You cannot place the lone pair here like this instead of writing F. No, that is not correct. So this will be F, and lone pair, that will always be in equatorial position, not axial position. Okay. Now without the lone pair, if you focus on the remaining shape, so as if it is like this. So this type of structure, just follow this, and there is a lone pair. So if you just consider this is known as seesaw, and that is drawn in the, this is the picture. So here it is drawn in this way, but if you just rotate it, it will be like this. So that is why it is seesaw, it looks like this here. Okay, so this is the next possibility. Now here the angle is slightly different because as you are you have replaced one bond pair with a lone pair. So obviously there will be some LP-BP repulsion. So angles will be changed accordingly. Okay, so here the angles are now changed from 120/90 to 102/173. Though molecule to molecule there may be slight difference, but more or less it is like this. It cannot be exactly 120 degree or exactly 90 degree, because there will be some repulsion between this lone pair and bond pair, which is 90 degree. Okay, come to the next one, AB3E2 type. So when it is AB3E2 type, now we are having two lone pair. Corresponding example, ICl3, and it is T shape. So T shape, why? Because again take the example of PCl5. Just imagine the example PCl5. Now two positions there will be lone pair. So this position there will be lone pair, another position there will be lone pair. So this is the remaining structure. So the remaining structure, it looks like T. So just rotate it, it will be looking like this. Here it is written in this way. I mean drawn in this way. But two lone pair if you place in the equatorial position, because lone pair you always have to place in equatorial position, then the remaining geometry, or better I can say remaining shape, it will be like a T, letter T, and angle will be 90 degrees, because this angle there is you cannot consider angle with bond pair, we only consider angle between three atoms. So this angle is 90 degree. Example is ICl3, where I is A and 3 chlorine atoms, there are 3 B atoms. So this is PCl5. You can see it is just like the first example in the below left hand side. Okay, trigonal bipyramidal. So if I draw it here, if you join these three positions, you are getting a triangle, and if you join this part, you are getting two pyramids. So that is why the name is trigonal bipyramidal, two pyramid, bipyramid. Then okay, let me draw it. SF4 I have already done, and if it is ICl3, so this is the triangle, two lone pairs you have to place. This is chlorine, this is chlorine, this is chlorine. So if you just focus on this part, if you just focus on this part without the lone pair, it looks like T. Okay, and this angle 90 degree, this angle 90 degree. Next is AB2E3. So when it is AB2E3, there are two bond pair with two B atoms and three lone pair. So XZF2, just you have to just remember the parent structure. The parent structure is, I mean to say, AB5. Example is PCl5. Now in this case, now as there are total three lone pairs, so all these positions there will be lone pair. So the remaining structure is like linear shape, isn't it? So XZ, all these triangular position there will be lone pair. And this is a fluorine, this is a fluorine. So if you consider only XCFF part, if you focus on this part only, it is linear, isn't it? The angle is 180 degree. And the next example is possibilities ABE4, though that is very rare. And now we have seen many examples, but one question may arise in your mind that here examples are directly there. And it is already mentioned that it is seesaw, it is T-shaped. So it is already information is given there. But suppose a molecule is given, then how you will decide that which one will be trigonal pyramidal, which one is seesaw. So see how we will do this. So just take this example ICl3. So ICl3, here the central atom is, just compare with AB3E2. Okay, though at a first when you will be getting a new molecule, though it is given already there, so that is why I am writing AB3E2. But when it will be something new to you, you will not be able to understand which type it is. So how to understand that? So here, if you consider this is a central atom, another question may be there: how to decide which one is central? Now see, central atom is always that atom which is lesser in number. If you look at all these examples, only P4 5 chlorine, only one sulfur 4. So only you have to choose that one which is larger, less in number. So it will be larger, less in number, and also more electropositive compared to other atoms. So I is more less in number, larger in size. Now I, how many valence electrons are there? I is from group 17, and group 17 means total 7 valence electron. Now out of these 7 valence electron, as you can see, 3 chlorine. So I'm just drawing the structure. Suppose I do not know whether it is which type it is, which geometry it is. I do not know. So under that condition, they simply write 3 chlorine. So obviously, out of 7 valence electron, 3 will be used up in bond formation. So how many are remaining? 7 minus 3. 4 electrons are remaining, right? So these 4 electrons that must be treated as lone pair. So in this way, now you can understand if you are doing this type of checking. I will not say it calculation. It is a type of checking. Consider the central atom. Next step is you have to know its valence electron. Once you know the valence electron, you have to next check how many bond pairs are there. So 3 bond pairs are there. Basically, sorry, 3 electrons it is using. So that is why there are 3 bond pairs. And as 4 electrons are remaining, so there will be 2 lone pair. So total positions are 3 plus 2. So total positions will be 5, right? And 5 position means it will be under this category. And as it is 3 BP, so it will be AB3 and 2 lone pairs. So AB3E2. Okay. So in this way you can understand under which category it will be there. So it is a one way of doing this, but there is also a formula that will while solving any problem that will help you. But this is the basic theory, that is following any formula blindly, that is fine. During exam we don't have much time and we have to follow formula, but how the formula is generated, what is the actual logic behind it, if you understand that, your idea will be more clear. So the same thing you can also do for XEF2. So let's try XEF2. So for XEF2, suppose you do not know any geometry. So for Xe, as it is from group 18, valence electron will be 8. Now out of 8 valence electron, as there are 2 fluorine atoms, that means you have to consider 2 xenon fluorine bond. So 2 xenon fluorine bond means 2 electrons will be used up. So out of 8, 2 electron used up in bond formation. Remaining electron 6. That means total 3 lone pair. So again see 2 and 3, total 5 positions. So 5 position means it will be under electron pair category, total 5. And it will be trigonal pyramidal geometry. But as you do not have total 5 bond pair, so trigonal geometry, what you will do, just write, draw the central atom, then this triangle shape you can draw. These are the 2 positions. Now you have to place fluorine atom and all the lone pairs. So fluorine atom you will be placing, okay, first place the lone pairs. Lone pairs will always be in equatorial position. You cannot place it in axial position. Okay, and these 2 are the position. So in this way, if any new molecule is given, you can draw the structure by considering its valence electron. And after that, out of this valence electron, how many used in bond formation, how many used in lone pair formation. In this way, final geometry you can understand. Once you know the final geometry, then without the lone pair, what is the remaining shape, all these things you can understand. And once you know the shape, you can also get the idea about the angles. If it is perfectly trigonal bipyramidal where you do not have any lone pair, it will be simple 120/90. But when lone pairs are present, there will be LP-BP repulsion or LP-LP repulsion. So angles will be slightly changed. So after electron pair 5, next we will see what will happen if electron pair total 6. So when it is 6, maybe all these 6 electron pairs are treated as bond pair. Example is, the general formula is AB6 and here it is octahedral. And example you can see, you can also draw it like this. Suppose this is a square plane and these 2 are the axial. But see, you can also imagine it in another way. If you, rather than joining this fluorine, you can also join these 4 fluorine. Then also you are getting a square plane, right? Or you can join these 4 fluorine. So different possibilities there. You can look at different angle to this one. Next one is 5. That means 1 lone pair will be there. AB5E. So when it is from octahedral, one position you are changing by a LP. So now it will be like this, and now it is square pyramidal because This is the square. Now it is not symmetrical. The previous one is symmetrical. Octet, you just have 190 degree. All the positions, that is, if you compare this two fluorine, obviously their angle is 180 degree. But if you consider any fluorine like this, then it is always 90 degree. Okay. So when it is 90 degree, we call it cis. But if you consider any two fluorine having angle 180 degree, then we call it trans. Don't call it axial, we call it trans. It is these two fluorine, they are trans to each other. But when the angles between two fluorine, in this case it is fluorine, it is 90 degree, then it will be, their relationship is cis. So in octahedral geometry, cis trans, this is common. But what we are discussing, if one position, one atom you are just replacing with a lone pair, now it will be changed to square pyramidal. So now you can draw a square, and if you are joining all these atoms, you are getting a pyramid. So that is why the name is square pyramidal. Angle will be slightly lesser than 90 degree because there will be repulsion with this lone pair bond pair repulsion. So these angles, it will be slightly lesser than 90 degree. It is no longer the ideal angle. Example is IF5. So for IF5, we know there are total 7 valence electrons for iodine, the central atom, out of which 5 electrons will be used up for bond formation. Remaining electron 2, which will be treated as one lone pair. That means total 5 bond pair and 1 lone pair, total positions will be 6, which we are discussing now. Okay, but as there is one lone pair and you have to place that lone pair in this position. Okay, you can also place it in this position, but that will make the same structure, equivalent structure. Next is if you have 4B and 2E. Corresponding example, XeF4. So XeF4, Xe out of we know 8 valence electron out of 8, as there are total fluor xenon fluorine bond. So 4 electrons will be used up and there will be total 4 bond pair. Remaining electron 4, that means 2 lone pair will be there. Okay, so 2 lone pair, the lone pairs, they must be far from each other because between 2 lone pair there is maximum repulsion. You cannot place these 2 lone pair like this. You cannot place it like this. So now the angle is 90 degree. You have to place it as far as possible. So it should be like this. So their position should be always 180 degree. That is, they should be trans to each other. And these are the positions of fluorine. So it is derived from octahedral geometry. That is a parent geometry. But if you ignore these 2 lone pair, without this, the remaining shape will be simply square planar. If you just focus on this part. So that is why it is written square planar. And now you have 2 different types of angle. But when it is SF6, that is the ideal situation where you do not have any lone pair. In that case, we talk about only one angle. But now there are 2, that is, you have to decide where to place lone pair, where to place atoms. And then we have AB3E3. So 3, this is also very rare. So example you are not seeing here. But if it exists, now to axial positions we have already, it is occupied by lone pair. So you have to choose here. And without these 3 lone pairs, if you look at the remaining position, it is like the letter T, isn't it? And the angle will be slightly lesser because of repulsion between LPBP, but this is 180. Now we have seen electron pairs starting from 1 up to 6, though there is another possibility which is 7, but for your syllabus, if you learn up to electron pair 6, I think that is enough. So if we summarize it, it will be like this. So see, starting from here, it is starting for true because 1 electron pair that we mostly do not deal with, and it is ending at 7, though we have discussed only up to 4, up to 6, but the next possibility is 7. So when it is 7, it is basically pentagonal bipyramidal. Up to this we have discussed in detail, but when it is 7, pentagonal bipyramidal. So how it will look? Suppose AB7. So it will be like this. Just draw a pentagon. So there are total 5 positions. Remaining 2, 1 and below. So in this way AB7. But suppose if it is there is one lone pair, it will be pentagonal pyramidal. So this position is now there. If there is lone pair, the remaining position is just the pentagon and one pyramid, not bipyramid. Remember, triagonal bipyramidal. So it is just like that. Now it is pentagonal bipyramidal. That is the difference. So in this slide, basically we will discuss the limitations of VSEPR theory. So just we know any theory there is always some limitations. So what are the limitations? See, it is able to predict geometry of a large number of molecules, especially in which case it is more successful. You will see that especially the compounds of p block elements, it is really successful. But if you now move to transition metal compounds, that is the d block elements, then this theory we cannot apply. And for d block, how to decide the structure, that will be discussed in the corresponding chapter, which is solely for d block elements, separate chapter. Okay? But remember, it is mostly successful for p block elements. Then the theory gives geometry of simple molecules, but theoretically does not explain them, rendering its limited applications. So simple molecules, it is fine, but if the molecule is very complex in nature, then some problem may arise. Then directly you cannot apply this theory. So we can see some examples where we can find limitations. So here this molecule is, if you look, consider the formula, it is XeF2, right? So CF6. Now xenon is having 8 valence electron. Out of these 8 valence electron, as there are total 6 xenon fluorine bond, so 6 bond pairs should be there. That means 6 electrons are used up. Remaining electron only 2. So there will be 1 LP. So total position 7. So it should be pentagonal bipyramidal. Remember the last structure that we have seen in the table, just in this slide. So now if it is pentagonal bipyramidal, the structure should be like this. Just make a pentagon. And this is another position. And just 180 degree to it, there is lone pair. So this should be the ideal geometry, right? But actually this structure is not the experimental structure. Experimentally it was found that the structure is not PBB but distorted octahedral. This type of geometry experimentally found. So why we are calling it distorted octahedral? See, it looks like octahedral and the lone pair that is present, as if it is, if you draw this pyramid, as if it is protruding from this pyramid in between this, just as if it is in the middle of this triangle. I'm talking about this triangle. So it is coming out of this triangle like this. So it is not exactly octahedral because of the presence of this lone pair, there will be some change in, that is, these bonds will be shifted from their original position. So that is, it is not perfect octahedral, it is distorted octahedral. Some more examples where we can see that VSEPR theory does not predict the correct structure. Some more I will write here. IF6 minus, XeF6 you have already seen. Then FeF6 2 minus. So in these two cases, distorted octahedral, this type of structure is seen. And remember here the lone pair, it is inactive. That is for structure determination, it has no direct rule. and some more limitations also present, which is BRF6 minus X6 SB antimony X6 minus, but this X is Cl Br I. Then it will be selenium X6 2 minus or tin SL6 4 minus. So all this structure, if you predict the geometry based on VSEPR, the structure that you will be getting, it will not match with the experimental result. So these are slightly advanced level. Probably you will not get any problem from this, but still, if you are interested, you can consider. XCF6, SNCl6, tellurium, TEF6. So all these you can see the central atom, that is from p block elements. Fine. And during discussion of one problem, probably in next 1 or 2 slides, you will see there is one formula. So if you apply this formula on these molecules, basically they are polyatomic ions, not molecules, all are carrying some negative charge, you will see the predicted structure from VSEPR, actual structure is. So for these two, it is, I have already mentioned distorted octahedral, but all these examples are drawn in black, they will be perfectly octahedral. But VSEPR is saying something else. So these are distorted octahedral, though ideal structure should be PPP. If you consider all these molecules in black color, it should not be perfectly octahedral, but actual experimental result is perfectly octahedral. That is the limitation. So now we'll discuss one problem. Which species has the maximum number of lone pair of electrons on the central atom? Now, as I have shown you, what you can do, you just have to choose the central atoms. In this case, it is chlorine for first one, then xenon, then sulfur, and then 3 iodine. So out of 3 iodine, 1 iodine you have to consider as if it is the central atom, right? And then you can do the calculation. So which species has maximum number of lone pair of electrons? So if you want to answer this, you have to know the geometry, how many bond pairs, how many lone pairs are there. Now, as I have already shown that, remember for XeF4 I have already shown it, that for Xe there are total 8 bond pairs. Out of these 8 bond pairs, 4 will be used up in bond formation. So there will be 4 BP, and out of 8, 4 used up, 4 remaining, that means 2 lone pairs will be there. So total position 6, but 6 means it should be octahedral. But in octahedral, you have only 4 XeF bond. So in octahedral, there will be only 4 positions are covered. Rest of the 2 positions, because octahedral means 6 positions, the rest of the 2 positions there must be lone pair. So in this way you can predict how many lone pairs are there. But there is also a formula, if you want to use that, you can also do so. Fine. So I will also do it for ClO3, because sometimes if you do not want to use that formula and you want to do it in this way, how to do it, I'm just showing that. So for chlorine, as it is from group 17, there will be total 7 valence electron and 3 oxygen. Normally what we know, oxygen always form double bond, but you have to just focus on sigma bond, not pi bond. So 3 oxygen means out of these 7, 3 electrons will be used up in bond 3 bond pair, that is a sigma bond I am talking about, and 3 used up, there is 4 electron remaining, right? But remember, there is also negative charge. So 3 involved in bond pair and 3 electron will be also involved in pi bond formation. So there is just remaining 1 electron. 3 used up in bond pair if you consider sigma. 3 also used up in pi bond formation. So we will ignore that. So 3 gone, only 1 is left. So this one and there is extra electron, so these two will be treated as if there is a lone pair. So there should be one lone pair. So this is one way you can do, or if you want to follow a formula, that also there. So what we do in this formula, we try to find out the steric number. Steric means, steric number is nothing but how many positions are there. So suppose if the steric number you are getting 2, that means central atom A, there will be total 2 positions. Suppose steric number you are getting 3, so there will be 3 positions. 3 positions, I'm telling it, covering both LP as well as BP. It is not only for BP, okay? So these 3 positions you have to cover when there is steric number 3, and 3 position you have to cover means there must be any atom or it may be lone pair. So this is actually steric number. And here the formula is steric number equal to half of V plus M plus minus C. So V is valence electron for the central atom. M means number of monovalent atoms. So it means if you consider ClO3 minus, oxygen is not monovalent, right? So in case of ClO3 minus, in place of capital M, you will just put 0 because oxygen is not monovalent. And then what about C? C means if it is positive charge, that is overall charge, if it is positive, though that is comparatively rare, you have to subtract it. If overall charge is negative, then you have to add it. So positive charge means subtract it. Okay. So in this case, we have 2 neutral species, XeF4, SF4, and we have 2 anionic species. So steric number, depending on what steric number you are getting, you will be having all these geometry. So that you can see in this table. Fine. So one by one, if we solve this, probably will not be able to finish it, but let's try this one. So for ClO3, overall charge is negative. Steric number is equal to half. Number of valence electron 7. Capital M will be 0, no monovalent atoms, and we will add one negative charge. So it is 8 by 2, that is 4. So it should be tetrahedral. So the structure should be like this. Remember tetrahedral, but in tetrahedral there are total 4 positions, but one position you have to place lone pair. So there will be one lone pair. Similarly, if you do this for XeF4, SF4, you will get result. And what about I3? So I will do it for I3 because it is to some extent different. So among these 3 iodine, one iodine considered as if it is central atom. So 7 valence electron, rest of the 2 iodine you can consider it as if 2 monovalent atoms and negative charge. So 9 plus 1, it will give you 10 by 2, that is 5. So it should be triagonal bipyramidal. But you have only 2 bond pair. So what you will do? Triagonal bipyramidal means there is a triangle. So all these positions there will be lone pair. Because total positions 5. You just have 2 iodine-iodine bond. So that should be like this. So in this way you solve the problem. All the structures you can see here. So in ClO3 minus there is one lone pair. Here XeF4 you are having 2 lone pair. Here also we have one lone pair, and this is total 3 lone pair. So which species has maximum number of lone pair of electrons on the central atom? It should be which example? It is last one, I3 minus. We are at the end of the session. Thank you for listening.